Okay, so today I'm going to be going over section 2 from chapter 5, which is, as I told you yesterday, is going to be explaining how what we learned in the last chapter on electron configuration, how that fits in with the topic for this chapter, which is the periodic table. And then after kind of going through how electron configuration is reflected in the periodic table, then I'll go over the blocks of elements and describing how they are similar. Okay, so the elements, of course, we know are arranged vertically in the periodic table into groups that share similar chemical properties, and the horizontal rows are called periods. The length of each period is determined by the number of electrons that can occupy the sublevels being filled in that period. And the reason why we have to understand why those two are related is through the number of sublevels that we have in each period, and the fact that the period number corresponds to our principal quantum number, or n. So for n equals 1, we have only one orbital, which is s, which you see here. Remember, each orbital can hold a maximum of 2 electrons. For n equals 2, there are 8 elements in the period because we have both s and p orbitals. There's one s orbital, but there's 3 p orbitals. The one s orbital can hold 2 electrons, and the 3 p orbitals can hold 6 for a total of 8. Same thing in period 3 for n equals 3. We still have 8 because the 2 sublevels of period 3 are at 3s and 3p. It's only when we get to n equals 4, or the 4th period, where we have an additional 5 orbitals when we include 3d. So in period 4, we have 4s, 3d, and 4p for a total of 18. There's 2 from 4s, there's 10 from 3d, and there's 6 from 4p. Then we go to period 5, and we have the same thing. We've got 2 from 5s, 10 from 4d, and 6 from 5p. When we get to period 6, now we have another set of sublevels to include. So we've got 2 electrons from 6s, we have 14 electrons from 4f, 10 from 5d, and 6 from 6p, which makes a total of 32. And the same for period 7, only it's 7s, 5f, 6d, and 7p. So this is how you relate the number of elements in each period to electron configuration. So just to go through that again, but looking at it at the periodic table. In the first period, we have n equals 1. For n equals 1, there's only one orbital, which is the s orbital, which holds a maximum of 2. So we only have 2 elements, hydrogen and helium. For the second period, which is n equals 2, we have the 2s sublevel, which is reflected in lithium beryllium. And we have the 2p sublevel, which can hold 6 electrons, which is why there are 6 elements in 2p. So altogether, the second period holds a total of 8 elements. Filling the 3s and 3p sublevels accounts for the 8 elements of the third period. And then when you get to periods 4 and 5, as I said, we're going to add 10 extra elements in the D block, as well as our 6p elements and our 2s elements for a total of 18. That applies to both periods 4 and 5. Filling the 4F sublevels in addition to the S, P, and D sublevels is going to add 14 more elements to the 6th period, which totals 32. The period of an element can be determined from the element's electron configuration. For example, arsenic, which is a chemical symbol As, has the electron configuration, or I should say the noble gas, to be more specific, the noble gas configuration of argon, 3d10, 4s2, 4p3. The 4 in 4p3 indicates the highest occupied energy level is the 4th energy level. Therefore, arsenic is located in the 4th period. Based on the electron configurations of the elements, the periodic table can be divided into 4 blocks, which I explained in the last chapter. This is why I wanted to introduce the periodic table in relation to electron configurations in the last chapter, because they are very closely related. So you are at least familiar with it because I talked about it in the last chapter. So again, we've got the S block elements in groups 1 and 2, P block groups 13 to 18, D blocks 3 to 12, and F block down at the bottom. So looking at the S block elements, groups 1 and 2. These are very highly reactive metals. Group 1 metals are more reactive than group 2. Can anybody think of a reason why group 1 would be more reactive than group 2? Okay, well, I guess I would start by saying, or by asking the question for you to think about, why do atoms react at all? What is the purpose of an atom reacting? Why aren't, actually, well, yeah, okay, so let's go from this. If I ask you, why aren't atoms reactive? Sorry, why are atoms reactive? Then you might think to yourself, well, what kind of atoms are not reactive? And the answer to that question, why atoms are not reactive, is because, or like what kind of atoms, God, I cannot like explain myself today. Let me start over. If I ask you why atoms react, you might not know, but then I would follow that up by saying, well, think about the kinds of elements that are unreactive. And there should be one group of elements that come to mind which are unreactive. And that should be the noble gases. So if I go, let's do this. In books, I think. Yep. Okay, so if I ask you again, the main question, just keep that in mind. The main question is, why are atoms reactive? Then I told you the second question you should ask yourself is, well, what kind of atoms are not reactive? And let's see why they are different from everything else. Why would they have a reason not to react? So again, the first thing that you should go to when I say which kinds of atoms are not reactive, you should immediately go to the noble gases. So next thing, why are the noble gases unreactive? Well, it has something to do with their electron configuration. So what's the electron configuration of helium? It's 1s2. How many electrons can 1s hold? 2. How many electrons are in helium in the 1s orbital? 2. if you look at neon, and I'm only going to do the outer shell, I'm only going to do the main energy level because those are the electrons that are available to react, the valence electrons. If I go to neon, we've got 2s2, 2p6. So of all of the electrons that are available to react, those are in level 2. And if you look at the configuration here, the orbitals are completely full. So why would neon react with anything? Why would neon change its electron configuration at all if its electron configuration at the moment is completely full? Argon, same thing. You've got the 1s2, 2s2, 2p6, and then you've got 3s2, 3p6. Again, a full outer shell configuration. So every other element on the periodic table does not have a full electron configuration in its outer shell. This is why elements are reactive, because all of, oops, I want to cancel that. Because all the rest of these elements are trying to be like that group. Whether that means that they have to gain electrons, whether that means that they have to lose electrons, whether that means they have to share electrons, in whatever way that they have to try to get a full configuration, that is why everything else is reactive. So back to the original question, why is group 1 more reactive than group 2? You have to look at its position relative to group 18. So let's take lithium, for example. Lithium has a configuration of 1s2, 2s1. Which of the electrons are the valence electrons? That is, because it has only one, that is the single electron that is in the 2s orbital. So if lithium can get rid of that one electron, it's going to have the same configuration as helium. It will be stable. If you look at beryllium, what is beryllium's electron configuration? 1s2, 2s2. So beryllium needs to get rid of 2 electrons in its outer shell, not just 1. So all of group 1, the only thing they have to do to have a stable configuration like group 18 is get rid of 1 electron. All of group 2 are going to have the same configuration. They're going to have a configuration of ns2, where n is equal to the period number. The entire group 2, they're going to have to get rid of 2 electrons in order to become stable. Now, we have a tendency to skip the transition metals because they're a little bit more complicated. You can see, just look at manganese. Manganese can have up to 4 different oxidation states, which means the transition metals have options. Let me put it that way. When it comes to how to get a stable configuration, they have lots of options. So we generally kind of skip the D block when it comes to how they react, because they're variable, very highly variable. But group 1, very stable in getting rid of 1 electron, and group 2 getting rid of 2 electrons. Now, since we're skipping the D block, we're going to go straight to group 13. Now, for group 13, if they want to be like the noble gases, they can either gain 1, 2, 3, 4, 5 electrons to be like neon, or they can lose 1, 2, 3. So especially for the metals, not so much boron. And I want to make that distinction because when we get to chapter 6, it's gonna come back in. So let's ignore boron because boron is a non-metal. If you hopefully learned from earlier grades where the metals and non-metals are split on the periodic table, it generally starts underneath boron, kind of comes down like that, something like that. So all of the elements to the right side are metals. Everything to the right is a non-metal. Everything to the left is a metal. And the elements that kind of sit right on top of those stairs are metalloids, which I think I did at the very beginning. But anyway, just for review. So basically, for group 13, you're talking about really those three, maybe even thallium, those four metals. They're going to form -3 ions. Oh, sorry. Oh my gosh. +3, because they're losing electrons. We're going backwards. So group 1, they're going to form +1 ions because they're going to lose an electron. Group 2 is going to form +2 ions because they're going to lose 2. Sorry, I forgot what I just said. Just to make sure, group 2 is going to lose 2 electrons to form a +2 ion. I don't know what my problem is today. Now, group 14 is an interesting group because they've got 2 choices. They either gain 4, 1, 2, 3, 4, or they lose 4, 1, 2, 3, 4, going all the way back around, 4. Both of those are very difficult. So group 14 has a tendency, especially these 2 guys, carbon and silicon, they have a tendency to form covalent bonds because they're like, you know what? Gaining 4 is hard, getting rid of 4 is hard, so we're just going to share. Okay, so that makes carbon and silicon very different. Once you get to group 15, though, you are closer to the noble gases on the right-hand side than you are to the left. So for group 15, they're going to gain 3 to form -3. Group 16 becomes -2, and group 17 -1. So these 3 groups are going to gain electrons to become stable, whereas groups 1, 2, and 13 are going to lose electrons to become stable. The bottom line, though, going back to, again, the original point, just to kind of tie together everything that we've been learning so far, the main point is that group 1 is more reactive than group 2 because they only have 1 valence electron to get rid of, whereas group 2 has to find something to take 2 electrons, not just 1. For example, like I said, I've already gone through this a little bit. Lithium is helium 2s1 and sodium is neon 3s1. So the single electron is easily lost and makes group 1 extremely reactive. There are 4 groups on the periodic table that have specific names, not just like group 1, group 2, group 3, whatever. Group 1 is called the alkali metals. In their pure state, they have a silvery appearance and they're extremely soft. If we were actually at school, I'd be able to actually show you IRL because I think I still have some sodium metal in the lab, but
whether you've left school or you're still at school, you can appreciate the sheer fun, mayhem that chemistry can be. There's so much to it. Bunsen burners, mixing chemicals. Very nice. Now, you may have been allowed to mix very small amounts of lithium with water. You may, if with a responsible adult, have mixed H2O with sodium. And you may, under very strict scientific control, have witnessed potassium mixed with water. The odds are, if you have, it will only ever have been on one of those rubbish science videos. There you go, my present. These next two are the dog's nuts of the periodic table. They are, if you like, the king and queen of alkaline metals. Mix these babies with water, stand well back, and watch the mayhem. And that's just what we're going to do. Mr. Tickle, bring on the rubidium.
Here it is.
Is that it?
Well, it might not look like much, Richard, but it's a highly reactive metal. It's sealed in this glass tube under argon atmosphere conditions, just for safety.
Right, so what's going to happen when you drop that in the water?
Well, imagine, if you will, letting off a hand grenade in a bathtub.
Righto, I'm off. Have that.
Okay.
Good luck. Okay, Tickle. Drop the rubidium in the water. 2 grams of rubidium will only react when our specially designed vial dissolves in the water, which gives John a few crucial seconds to get into our safety zone. That is more like that.
Just for reference, that was only 2 grams of rubidium. Okay, 2 grams. That is about the same weight as 2 paper clips, and it completely destroyed a bathtub.
Brainiac, you get that kind of science. But I believe we can go one better. There is one more alkaline metal we can use.
Yes, Richard, Cesium, the emperor of alkali metals, particularly nasty to go off at any time.
And that's it.
Oh, yes.
I like it already. Now, what's that going to do when it hits the water?
Imagine a depth charge in a bathtub.
Fair enough, mate. I'll leave it to it. Good luck.
Thank you.
Okay, John, go for it. Clear the area. As cesium sinks in the water, the rapid generation of hydrogen gas should produce quite an explosion. It does. Magnificent. And I think that concludes today's experiment. There is, I should say, one more, even more reactive metal, francium. But for some reason, they wouldn't let us have any of that. So there you go. Today's lesson: never mix alkali metals with water.
Okay, so that was just a demonstration of the reactivity of the group 1 metals. They started with lithium, which is the first alkali metal, and then going down for sodium, potassium, rubidium, cesium, and francium, which they can't have because it's illegal. So these guys are so reactive, you cannot find them in nature as free elements. They're always going to combine with other elements to form compounds. The elements they combine the most strongly with, does that make sense? Whatever. Non-metals, obviously, because non-metals are going to be happy to gain electrons, like I was explaining before, to be like the noble gases, whereas the alkali metals really want to get rid of 1 electron. So the absolute best combination of metal non-metal is group 1 with group 17, because group 1 really wants to get rid of an electron, just 1, and group 17 really want to gain 1 electron. And as you saw from those videos, all they were doing was adding the metal to water. They react with water so strongly that they have to be stored in oil. This is part of what gives them their name, the alkali metals, because when they react with water, they produce hydrogen gas and alkaline solutions. So they have to be stored, like I said, in kerosene or oil.
If we continue down the column to potassium, we see that the potassium metal is also stored under mineral oil to minimize its reaction with the oxygen in the air. If we remove a piece of potassium metal, we can see that the potassium is coated over with a gray coating of the oxide. As we continue down the column, group 1 metals get softer and softer. The potassium cuts very easily. As we cut through the metal, we expose the shiny metal surface underneath. The potassium is extremely soft. We can easily flatten out the potassium metal. It has a consistency of cream cheese. The potassium is a metal and is an excellent conductor of electricity. If we add a piece of potassium metal to water, we see that it reacts much more rapidly with the water than the sodium. As you go down the column, the ionization energy decreases and the metal reactivity increases. The reaction is very exothermic, and the hydrogen that's produced ignites. We can test for the formation of potassium hydroxide.
Oh, I'm sorry. I'll fix that. I was trying to go back to the periodic table because he's going to make a really good point here. And let me just show you really quickly what I mean. So he's talking about going down the periodic table. Is that going to share my iPad? There we go. So he's talking about the alkali metals. He's talking about going down the periodic table. So in the previous video, we saw rubidium and cesium. Rubidium was the first explosion, and cesium was the one where it literally just blew the whole bathtub apart. Sodium and lithium are going to react with water, and he's doing potassium right now. But the main point is that as you go down this group, they become more reactive, meaning the reactions are much more exothermic, they're much more violent, they're much more energetic. And you will be learning more specifically about ionization energies next week and why that is. But basically, I just want you to think about where are the valence electrons as you go down this group, because what's changing if all of these elements are S1 elements, the only difference is the main energy level that one S electron is in, like that single, not the number one, but the single electron that's in. So lithium, the electron it wants to get rid of is 2s1, sodium 3s1, potassium 4s1. So what does that mean if I say from 2 to 3 to 4 to 5 to 6 to 7? It's one of the original points that I brought up way back at the beginning of chapter 4, which is the higher the principal energy level, the further away from the nucleus that orbital is. So the cesium, the single cesium electron in 6s is much further away from the nucleus than the single electron in 2s for lithium. So what does that mean? If you're farther away from the nucleus, you are two things. You are shielded from the nucleus by all of the inner shell electrons. All of these other electrons that are in levels 2, 3, 4, and 5 are shielding the 6s electron for cesium. And also it's just a physical distance between that lone electron and the positive nucleus. So we'll talk about that more in detail as we go through the periodic trends. But I just wanted to introduce that because he's talking about it in the video. So we'll go back to the video.
To water, we see that it reacts much more rapidly with the water than the sodium. As you go down the column, the ionization energy decreases and the metal reactivity increases. The reaction is very exothermic, and the hydrogen that's produced ignites. We can test for the formation of potassium hydroxide by adding phenolphthalein. The solution turns red-purple due to the formation of potassium hydroxide.
Okay, so I want to pause it there because I know we haven't done chemical reactions or formulas yet. Oh, sorry, yeah, equations. That's the word I'm looking for. But I'm sure you've all seen a chemical equation before. So this is the reason that these metals are called alkali metals, because when they react with water, they produce hydroxide and hydrogen gas. The hydrogen gas is the smoke that you saw coming off of the top of the beaker. And because hydrogen gas is highly flammable, I can't draw fire because it ends up looking like a plant, but anyway, that's my fire. Hydrogen gas is highly flammable, which means that as the potassium continues to react with the water and create sparks, sometimes you see it burst into flames as well. But this has a very high pH because it's a hydroxide, which is that OH. And so that's what makes them, that is why they are called alkali metals. Yeah. Okay. That's group 1. Group 2, keep it on time. Group 2 is called the alkaline earth metals. So that's beryllium, magnesium, calcium, strontium, barium, radium. They are going to contain a pair of electrons in the outermost S sublevel. These metals are going to be harder, denser, and stronger. They're going to have higher melting points and be less reactive, less reactive than the alkali metals, but they're still too reactive to be found in nature as free elements. So they're still going to react with elements in nature. For example, in the picture on the left-hand side, we have pure calcium but in nature, we usually find calcium as something called lime, I think, which is calcium oxide. And it's one of the components of marble, and that is a big block of marble that you see here. Okay.
In this video, we will move down group 2 of the periodic table, looking at reactivity.
Oh, crap. Okay. Ooh, put it back in because it's not better. So again, group 2 is going to have the same pattern. They're going to become more reactive as you move down the group for the same exact reasons as group 1, and they're just going to show you the difference.
In this video, we will move down group 2 of the periodic table, looking at reactivity. The first metal in group 2 is beryllium, which is highly toxic and unreactive to either water or steam. The next metal down is magnesium. Magnesium reacts very slowly with cold water, but does react with steam, which we can see here. It forms a gas, hydrogen, which can be easily lit. And also the white powder, magnesium hydroxide, which can be seen here. After magnesium comes calcium, which does react with cold water, fizzing to produce hydrogen, and also the insoluble calcium hydroxide, which you can see precipitating out of solution here. We can demonstrate the production of calcium hydroxide by putting some calcium in universal indicator solution. As before, hydrogen is produced, giving a foam at the top of the cylinder. And also, as the alkali calcium hydroxide is produced, we can see that the universal indicator solution gradually turns orange, then green, then blue, showing that the solution has now become alkaline. If we continue down group 2, we find strontium. This has to be stored under oil to stop it being oxidized by the air. The oil on the strontium causes the reaction to begin slowly, but gradually it picks up, and we can see that the strontium is reacting vigorously with the cold water. The bubbles, as ever, are hydrogen gas. You can also see some white particles in the solution. These are the slightly soluble strontium hydroxide. The next metal in the group is barium. This is slightly more reactive than strontium, and the reaction with water looks much the same.
Okay, so again, even the group 2 metals are going to react with water to produce hydroxides, which is why they're called alkaline earth metals. Okay, so hydrogen and helium, they have special cases, even though hydrogen has a configuration as the same as the alkaline metals. They don't share the same properties as the elements of group 1. Hydrogen is a unique element and it is a non-metal. So oftentimes, sometimes you'll see a periodic table which actually takes hydrogen out of group 1 and puts it kind of in the middle. But most of them keep it on the left-hand side because it does have a 1s1 configuration, even though it's not a metal. Like the group 2 elements, helium has an ns2 group configuration, but it's part of group 18 because the highest occupied energy level is full. Because level 1 can only hold 1 orbital, which holds a maximum of 2 electrons. It has a stable configuration. Whereas if you look at the rest of the group 2 metals, they have completely empty p sublevels. And that's why they are different than helium. I am going to skip the sample problems for now and go straight to, where is it? The D block. I want to make sure I cover it before I go back and ask some questions. Okay, so D sublevel first appears when n equals 3. And again, for the energy level, D is n-1. So even in period 4, we only start 3D. Each D sublevel has 5 orbitals, maximum 2 electrons each. So 10 elements or 10 electrons for each one. In addition to the 2 ns electrons of group 2, the atoms have 1 electron in the D sublevel of the N-1 energy level for group 3. So the group configuration for group 3 is N-1D1NS2. So for example, if I change, okay, I gotta get out. Oops, gotta get out of here first. So I can see my mouse arrow thingy. Okay, so I was talking about group 3. Let me make that darker. So what was it? Group 3. It said the group configuration is N-1D1NS2. So N represents the period number, right? So let's say for period 5, group 3, you would take the 5 and substitute that for N. So that would be 4D15S2. That's all that means. You probably, I don't know if you'll ever really see group configurations, but it's just good to, I guess, kind of go through so that you understand how configuration works when it comes to the periodic table and the groups there. Okay, and then you go through all of the groups and you would just increase that. Let me go back to here so I can draw. All right, so for group 3, we have N-1 D1NS2. Group 4, all you're going to do is add 1 electron to D until you get to, of course, 6. So you're going to have D5NS1 because this is one of your exceptions, right? When you take out one of the electrons from S and you fill in the 5th D orbital. And it goes all the way up to, I guess do the rest of them. So you got N-1, and then you've got D5NS2, group 8, N-1, D6NS2, 9, N-1, D7NS2, N-1, D8NS2. And then again, group 11 is your second exception, where you go D10NS1. And then finally, group 12, N-1, D10NS2. Now, one thing that I do want to point out, something that you can kind of figure out. Can I get rid of that last? Yeah. Oh, why did that not disappear on the screen? Anyway, one thing you can figure out for the D block. All right, this is the D. Oh, there it is. The D block. For group 3, if I add the total number of electrons from D and the S, I get the group number. Same thing for 4, D2S2, 4, 5, D3S2, 5, group 6, D5S1, 6. See a pattern? 7, 7, 8, 8, 9, 9. So for groups 3 through 12, if you add the number of electrons in the D and the S, you get the group number. So a really simple test would be if I say an element has the configuration 5D6, 6S2, what group is it in? All you have to do is add 6 and 2 and say it's in group 8. Easy peasy. Okay. Right, so I just finished saying that the sum of the electrons in the S and the D levels is equal to the group number. So if you look at iron, it has an outer configuration of 3D64S2. All you do is add 6 and 2 and you say it's in group 8. And of course, we call these transition.
The
middle body area of the table is made up of a nice solid rectangle of transition metals. These are the metals you think of as metals, with iron and nickel and gold and platinum. The majority of elements are metals. They're fairly unreactive, great conductors of heat, but more importantly for us, good conductors of electricity. They're malleable and can be bent and formed and hammered into sheets, and they're extremely important in chemistry, but overall surprisingly similar to each other.
Okay, so those are just some general properties of transition elements. As he said, good conductors of electricity and heat. They have a high luster. If you remember, luster is shine. They are less reactive than alkali and alkaline earth metals, of course, because they're more complicated. Some of them are so unreactive that they do not easily form compounds, and they exist in nature as free elements. If I were to show you periodic table, and I were to say, let's find the transition elements that are found free in nature, does anyone have any ideas which transition metals those might be? I will give you a hint. They are expensive because they are found in nature as pure elements. And they're all right next to each other in the periodic table. So first, we've got silver. Underneath that, we've got gold. And just to the left of that, we got platinum, right? We call these the precious metals. They are unreactive, so we can find them, like literally like go out into the ground and dig them up pure, even though they're transition metals. Okay. Right, two more properties of metals, specifically transition metals. They are malleable. Malleable means that you can beat them into sheets, like you can turn them into cans. Ductile means that they can be pulled into wires, like you've got, like, you know, just electrical wires. Let's see. That's fine. Anyway, just to make a long story short, you can see how the blacksmith uses malleability to make things flat. And then here's ductility. So this is key right here. So you started out with a 1 centimeter thick rod, and they pull it out to a wire that's 2 millimeters in diameter. That's ductility. Here are 3 other examples of transition elements, and I just wanted to show you this is what I mean by luster. This is like, they're really shiny. Of course, we know metals are shiny. And I want to get to the F block. Oh no, I haven't even done P yet. Oh my God. Okay. I'm going to do the P block. I'm going to skip the F block because we generally ignore them anyway. Okay. P block groups 13 to 18. Of course, we're filling the P sublevels. All right. So the big thing here, these are referred to as main group elements together with the S block. So P and S block are main group elements. Okay, none of that is really important. The only thing that I do want to mention is a trick. This is the trick I wanted to talk about. So for groups 3 to 12, the transition metals, you can add together the D electrons with the S electrons to get the group number. For groups 13 to 18, it's group number minus 10. And that gives you the number of valence electrons. So if I say fluorine is in group 17, how many valence electrons are available? You would just do 17 minus 10, and you would say there's 7. And of course, we know for the P block, the maximum number of electrons that are held there are 8, which means that it needs 1 more to be like the noble gases. Okay, bromine's another example. So just a couple of shortcuts a couple of shortcuts between electron configuration and group number. Okay, blah, blah, blah. It doesn't really matter. A lot of the P block elements, they have varying properties, which is why you can't really say specifically. This is what I was talking about earlier when I mentioned these are the nonmetals, and oh, that should be yellow. The nonmetals, I don't know why boron's not in there. Boron should be nonmetal. Here you got the metalloids and the metals. So the P block has all 3 nonmetals, metalloids, and metals. Halogens are kind of the opposite of group 1 in that they're very highly reactive like group 1, but they're highly reactive because they really need 1 electron. And one thing I want to point out before I go, because now it's 12:20, is when you have a non-metal plus a metal, actually, let me redo that because metals come first. This is something that is going to come up a lot. Now, when a metal and a non-metal react, they form a salt. And I don't mean like, I shouldn't write capital A salt, right, lowercase a. And what I mean by a salt is that a group of compounds that are the result of a metal and a non-metal reacting, those are called salts, right, which is here. Now, unfortunately, as human beings, we've decided to name one particular salt, salt. So that provides a kind of a problem because NaCl is not the only